Number 2? Okay, we can do number 2. All right, how about number 5? I'm not even trying anymore. Okay, how about number 9? 11, 13, 15, 17, 19, 17. All right, 23 and 27. 27? Okay. All right, let's go over these real quick. I want to be sure that you understand how to do it before I collect it from you. And again, when it comes time to collecting it, we're not going to have mass chaos going towards the folders. Just at the end of the period, go put it in your folder when you're done. I don't know if anyone went on Blackboard. You know where I showed you where the objectives were for this unit? I attached a document that has the homework audit on it so that you can start seeing what papers I need. Okay? Most likely over maybe next time I meet with you, or maybe even the time after that, we can pull the folders out and you can see what we've got and what's missing. All right. All right, so let's start with question number 2. For question number 2, you need a picture. So let me put the book underneath the camera so you can see what's going on here. All right, so you've got these 4 pictures, and they're asking what kind of intermolecular attractive force is shown in each of the following cases, and then predict which of the 2 interactions are stronger than the other 2. All right, so let's start with this first one, A. What do you notice about A? There is a hydrogen on one atom, right, magnetically attracted to a fluorine on another atom. What do we call that? Hydrogen bond. All right. For B, you've got 2 fluorine molecules. Both of them are perfectly symmetrical, so both are nonpolar, but yet they are still capable of sticking to one another. What is the interaction that allows that? London forces. One of the things that I really should have stressed last time, I don't think I did, London force. Everything has London forces. If you have hydrogen bonds, even though the primary interaction here is a hydrogen bond, these things also have London forces happening in the background. Everything has London forces. Just by the mere fact that they have electrons, maybe not the electrons that are involved in the hydrogen bond, but the other electrons that can shift to one side and create dipoles in other parts of the surface of the molecule. All right? All right, how about this one? This is one that wasn't in the POGL. We have a cation, something that is positively charged, and that's a permanent charge because this sodium has permanently given up its electrons to the environment, right? The positive charge on that sodium ion is magnetically attracted to the oxygen on water. And that oxygen, since it's electronegative, probably has pulled the electrons away from the hydrogen and created a negative charge over there. Right? What do we call this kind of interaction? It's called an ion dipole. It's the same thing as a dipole-dipole. The only difference is that in a dipole-dipole, the 2 things that are attracted, those charges are temporary. In an ion dipole, one of the guys has a permanent charge, the other guy has a temporary charge. All right, and then finally this last one, SO2. These 2 SO2, these sulfur dioxides, are asymmetrical, right? So if I were to draw a horizontal line across that sulfur right there, right, the top would look different than the bottom. So they're both asymmetrical and polar. There's a magnetic attraction happening between the negative charge on the surface of that oxygen and the positive charge on the surface of that sulfur. What is that attraction called? Is it a hydrogen bond? No. What do you need for a hydrogen bond? Hydrogen on one side, and on the other side you need either nitrogen, oxygen, or fluorine. That's neither of those cases, right? So what do we call this interaction instead? It's called a dipole-dipole, all right? So now we have to rank them from strongest to weakest, right? Let's start with the weakest. Which is the weakest one? London, right? Which is the next weakest one? No. Dipole-dipole? No. Then hydrogen. And then ion dipole. Think about it. These dipoles only happen, these charges on the surface of the molecule only occur when the electron happens to be pulled more so in one direction than in the other. That might not happen 100% of the time. So the charges only appear when the electrons move to one side. There are times when the electrons go back to middle. And when they go back to middle, those charges disappear. Here, that charge is always there. So this is going to be stronger. Simply because it's always there. This is permanent. All right? The charge here comes and goes and comes and goes and comes and goes, depending on whether the electrons are moving to the right place or not. Okay? All right, let's take a look at the next one. Question number 5, was it? Did you ask for that? It says you have these two molecules. They have the same molecular formula, C3H8O, yet they have different normal boiling points. So you guys would call these resonance structures, and in organic chemistry we call them isomers. This one has a boiling point of 97.2 degrees. This one has a boiling point of 10.8 degrees. All right, so which one has a higher boiling point? Which one, guys? The one on the left. All right. What does a higher boiling point tell you? It has much stronger intermolecular forces. Perhaps it has more intermolecular forces. Because it's not always about strength. You can have weak ones, but if you have a ton of them, that could be more impactful.
Does that mean it also has like a higher atomic weight?
No, they have the same atomic weight because they have the same 3 carbons, 8 hydrogens, 0 oxygens. It's just how they're linked together. All right? Okay. So, why would this be able to either make more intermolecular forces or stronger intermolecular forces? Well, what kind of intermolecular force would you expect to happen here? You got that little red dot. What does the red dot represent? Oxygen. If you have another one of these molecules sitting next to it that looks just like it, what's the oxygen? Is it going to stick to something? What is it going to stick to? This oxygen can potentially stick to maybe that hydrogen, right? What do we call that? Hydrogen bond. Do you think that maybe propanol has a higher boiling point because it's capable of hydrogen bonding and doing it better than that guy? Can this guy hydrogen bond? Does it have oxygen in it? Would an adjacent molecule have hydrogen in it? This can hydrogen bond as well. But obviously it doesn't do it nearly as much as that guy. Why? Take a look at the structure. Where is the oxygen on this molecule? Is it dingle-dangling on the surface? Yeah? What about here? This one's buried inside. So you're only going to form hydrogen bonds with somebody else if the parts that are involved in the hydrogen bonding are exposed. Here, this guy can make the hydrogen bonds, but that oxygen is kind of buried inside, so it might not make as many hydrogen bonds. All right, and so that's the explanation to this question. Are there other forces that are also present here? Do these things, are they also capable of London bonding? They are. They still have London dispersion forces, but the primary one that's making that boiling point really high is the hydrogen bond. Okay? All right. What was the next one that you needed to do? Yes, sir. on the end? It's not necessarily, well, the bond angle is going to be a little bit wider. It's just that it's on the surface and more exposed, really. I can pull models later and build these things for you, and you can compare. I think the bond angle might have something to do with it. All right, 17. 17's asking, which one do you want me to do? C? What's your question on it? No. So 17 is giving you a list of a bunch of different substances, right? GeCl4, CH4. I'm not going to do it because it's going to take some time to calculate this. It first asks what is meant by the term polarizability. So if you remember when we were doing that poll yesterday, things that are heavier, right, that have a higher molecular weight are capable of making more London forces. And it's not really the weight that's the issue there. The reason why heavier things can make more London forces is because they have more electrons in them, and therefore you have more opportunities for electrons to shift to one side. Okay? That's what's meant by the term polarizability. All right? So then they want you to put these in order of increasing polarizability. So the way that you do that is essentially calculate the molecular weight of each of these substances. The one that's the heaviest will, by default, have more electrons in it and be more polarizable. So you just have to look up the molecular weights of GE and then the 4 CLs off the periodic table and add them together and rank them from smallest to heaviest. So that's how you do it. Okay? You don't have to look at electronegativity values at all. It's simply on molecular weight. Then predict the order of boiling points of the substances. So the more polarizable, the heavier the molecule, the higher the boiling point. All right, assuming that there aren't other combinations of atoms in there that would allow you to form additional intermolecular forces like dipoles, and hydrogen bonds. Okay. All right, and then so that was 17, and then you guys wanted me to jump to 27, right? Okay, so 27. I like this question, and if you were to see anything on a free response, it's going to be like this. All right. They're going to give you 2 substances. And again, if we have time tomorrow, I'm going to pull out free responses for this section. If we don't do it tomorrow, we'll do it Monday. All right. They'll give you 2 substances, and they'll tell you some data about it. Or in this particular case, they asked you to look up the boiling points of these things. So which one of these 2 had a higher boiling point? This had a higher boiling point, and they also asked you to look at the melting point. Which one has a higher melting point? Would it not be water too? Okay. And then the question's asking which one has the stronger intermolecular forces. So which one has? I mean, when you're boiling something, you're adding energy to break these attractions, right? So if it takes more energy to boil these, what does it tell you about water? Has stronger intermolecular forces. All right. So why? What's the difference between water and H2S? This is capable of hydrogen bonding, right? And in this hydrogen bond, what happens is that the negative charge on the oxygen of one water will magnetically attract to the positive on the hydrogen on another, right? That's your hydrogen bond. This here is not capable of hydrogen bonding. The sulfur will still be negative, the hydrogen is positive, but this attraction is called something else. What kind of attraction is that? What's that? This is a dipole-dipole. And we learned that dipole-dipoles aren't nearly as strong as hydrogen bonds because of the fact that the elements involved don't have as huge of an electronegativity difference. All right, so they want to know for part B which solid is more or less dense. I'm sorry, no. They want to know if the solid of this stuff, H2S, is more dense than the liquid of that. Well, isn't it? Okay, what do you know about solids, liquids, and gases? In a solid, solids look like that, right? What about a liquid? The particles are more spread apart, right? What about a gas? Particles are even more spread apart. What is density? Isn't density a measurement of the packing of the particles? Right? Okay, so which one is most packed here? The solid is, right? Hydrogen sulfide looks like this. So the solid hydrogen sulfide is going to be more dense than the liquid. what did we learn about water? When water forms a solid, does it do it like this? No, how does it do it? It's a hexagon. Oops, try my best. I drew a pentagon. Look at that. I'm geometrically challenged. Okay. Solid water forms a hexagon. These are the hydrogen bonds in between the molecules, right? In the process of forming those hexagons, what does it do? It traps dead space. What about liquid water? Does it do that? What happens in liquid water? Are the particles kind of willy-nilly? Are they closer together? So in water, what can you say about the densities? Which one has a greater density, the liquid or the solid? The liquid has a greater density. All right. And water is the only exception to that rule. Every other substance, for the most part, natural substance, obeys this rule. Yes, Adi? That's a really astute observation. The answer would be yes. In biochemistry, you'll learn that the whole reason why DNA is a double helix is because the two strands form hydrogen bonds in between them. DNA is pretty geometric, right? When proteins fold, they'll either fold into like an accordion type sheet or in these helical structures. Pretty geometric, right? Entirely mediated by hydrogen bonds. Okay? All right, any other questions on the homework? Any other issues? No? All right, so let's make sure that goes in